This WaterLily tutorial is going to focus on more complex mappings and geometries. This time we're going to set up a two-dimensional simulation. You can see that here where we're using 2D tuples for the size and velocity. We are also going to define the Reynolds number and length scale like we did before. The main focus is going to be on the body, and we're going to use the auto body at first, and it's defined for a line segment SDF. But then also we're going to define a more complicated mapping. So what the mapping is really doing is it's mapping from some coordinate x to another coordinate psi. The purpose of the mapping right here is just to take whatever coordinate x we have, subtract off the location of the nose of that line segment, and then rotate it using that rotation matrix, which is just a function of some given theta. That mapped vector psi is then the input to the SDF. We find the closest point on the line segment to psi, then the length of that vector p is the distance from any point psi to the line segment. And that's all we need to define a 2D function in WaterLily. So we compile those and we generate a simulation using that makesim function. I've also included this viz file where I'm using glMackie and defining some visualization functions. And running that function generates this plot of the geometry, and if I run the simulation to update the flow and the geometry, I get this nice kind of interactive real-time simulation of the flow past this line segment at a small angle of attack. This is very pretty, but let's do something a little more advanced with the mapping by making this pitch up and down by changing the angle theta. So here I've defined theta 0 as the amplitude of the pitching motion and omega as the frequency, and I've replaced the constant theta with theta cosine omega t. Notice the t in the mapping is no longer grayed out because this mapping is now a function of time. I reevaluate the functions and make a new simulation and visualization. Now the line segment pitches in time, oscillating up and down. It's straightforward to extend this now to a full flapping motion, where we put this in terms of the maximum angle of attack and in terms of the Struhal number, and we also add a heave amplitude, which we include as an additional equation, which gives us a nice flapping motion with both pitch and heave. Next, we can generalize the way we made this SDF for the line segment. The way it worked is that we found the nearest point along the line, which is easy to do for a line segment, but we can also do for any parametrically described curve, such as an ellipse. So this is the definition of an ellipse of a length L and a thickness of 12%. To embed this parameter into the simulation, we can use the new parametric bodies package that I've developed, and actually this example is within that package. So here that body is defined in terms of the elliptical curve and a range of the parameter, so 0 to pi, as well as the mapping. We can run the simulation with no additional changes, but we see a weird geometry, and that's because we've only defined the ellipse halfway around, from 0 to pi. We can be clever with our map again, exploiting the symmetry of the geometry to reflect all of the negative points onto the positive side, and this will fix our geometric problem, resulting in a flapping ellipse. And of course, there's no reason to stop with an ellipse. We can easily define a NACA geometry, the NACA 0012, and use that to define a foil and get the flow around a flapping foil. The fact that we only have to describe one half of the foil actually speeds up the simulation a lot, and we can do this again using one foil to pretend to be two. So here's a second foil that we can add to the mapping, again without defining another geometry, just by checking if points are beyond a certain place, and if so, adding a phase shift to omega t and adding a spatial shift to the heave offset. And if we do that, we get this beautiful simulation of tandem flapping foils using one half of a NACA profile and some clever mapping.